All right, jumping into chapter 7. We're skipping 7.1. There's not really much to that section. We're going to jump straight into section 2. And the first few sections of chapter 7 are all about defining the Laplace transform. Okay, so this first section here in particular is just going to be a lot of definitions and theories about what the Laplace transform is and how we're going to use it. So let's just jump right in. With the definition here, so let little f of t be a function on the interval where we're going just from 0 to infinity. So it is important that we're only looking at the positive real number line here. The Laplace transform of our function f is going to be the function capital F defined by the following integral. All right, so where this integral comes from, not super important. It's more important just knowing how to use it. So this is going to be our transformation. Our transformation we're going to define as capital F of S. So S is this new variable that we're doing, and we're defining this to be equal to an integral here. My integral is going to go from 0 to infinity, so this is going to be an indefinite integral of this e to the negative st, and remember t is the variable of the original function, times our original function f of t dt. Okay, so this indefinite integral is what we're going to define to be our Laplace transformation. We're going to take our function, multiply it by e to the negative st, and then we're going to anti-differentiate t as the integral goes from 0 to infinity. Okay, so before we do some examples, let's just kind of really dive into this a little bit. Let's look at the domain of this Laplace transform function that we're creating. The domain of f of s is all the values for s for which the integral exists. So this may not exist everywhere. We only care about where this thing exists for certain variable or certain values of our s. There is a notation to this. And I struggled a lot with how to write out this notation because Word is just not the best for this, but I did find this. So the Laplace operator is always like a capital cursive L value of f. So this capital F and then this symbol, this cursive L of f is the same thing. I'm going to pull up the book here just to show you what it's really supposed to look like. I didn't really feel like diving too much into Word to find it. So here you go. Let me zoom in a little bit. So there you go, like a really curvy L. So this is the Laplace transformation of the function sine of bt. And we'll go through the examples here on our own here in just a second. But it's just the notation. The Laplace transformation of the function is the same thing as just capital F of s. Okay. So let's just do it, and we're going to jump into some examples. So first example here, determine the Laplace transform of, and we're going to start off very simple. We're just going to look at the Laplace transformation of a constant function f is equal to 1. And to do that, right, that means that we're going to find f of s, where f of s is going to be the infinite integral from 0 to infinity of that e to the negative st. This is going to be times 1 dt. So this is really just the integral of e to the negative st. That has an antiderivative of negative 1 over s. That's going to come down. And then still multiplied by that e to the negative st. All right, so there's the antiderivative. And now we still need to take this as it goes from infinity to 0 here. So from infinity to 0. Or, oh, sorry, that's backwards, right? From 0 to infinity. I guess that's better. Okay, if I plug infinity into this, remember we're plugging infinity into the t's, since that's the variable of integration. This is just going to be 0. Right, so if infinity, I plug in for the t values, it's going to be 1 over infinity because this is really in the denominator, so it just goes to 0. That's going to be minus plugging 0 in for the t, which is going to make this e value go away, and we're going to end up with negative 1 over s. Okay, and then this simplifies down just to be 1 over s. Now we do have to be careful because it doesn't exist everywhere. This is going to be the Laplace transformation for the function 1 with domain s has to be greater than infinity. Because s cannot be equal to 0, and also remember that we're only looking at positive values anyway. Oh geez, I said s is greater than infinity? That was dumb, sorry. S is greater than 0 is what I meant to say. So s is greater than 0 because it has to be positive values. Okay, so that's it. If I have the function 1 over s is what we call the Laplace transformation of the function 1. Let's look at another example, just making it a little bit more complicated. Determine the Laplace transform of the function f of t is equal to e to the at, where a can just be any constant. It doesn't matter what it is. So same thing as before, right? F of s is going to be my integral. This is going from 0 to infinity of e to the negative st times e to the at dt. We can multiply these two things together just using a product rule for exponents here. So we're still looking at the integral, sorry about that, as we're going from 0 to infinity. Okay. And then when I multiply these two things together, I'm adding the exponents, and I'm going to take this a little bit further. So when we add the exponents, I'm going to factor a t out of that. I'm going to write it like this. Okay, so this would be negative st plus at, but I'm going to factor out a negative sign, and we're going to write it as s minus a times t with the negative that's been factored out. Okay, remember the t is what we're doing the antiderivative for. So this has antiderivative. Let me get my little special thing here so we can write it really nice. Cool. All right, so this is going to have antiderivative of negative, so that negative comes down from the exponent here, and it's going to be the reciprocal 1 over s minus a. And then we're just going to leave the thing alone, e to the negative s minus a of t. And then this we're evaluating from, again, 0 to infinity. Right? If I plug infinity into that, the same thing's going to happen as before. This whole thing is just going to go to 0 because this is really in the denominator, and I'm taking 1 over e to infinity. That's going to be minus plugging 0 in for the t, which is going to make this e term go away, and we're going to end up with negative 1 over s minus a. My double negatives cancel out, and we end up with just the reciprocal there, 1 over s minus a. And again, we have to be careful about where this exists. This only exists for s values that are greater than a. Otherwise, it's going to give us negative values, or if s is equal to a, it's going to give us an undefined solution, which is not what we want. Okay, so cool. For my original function, e to the at, the Laplace transformation is 1 over s minus a, which notice is pretty close to the one from before. It just has that extra minus a there in the denominator. We're going to do one more here in this video, and then we'll do some more in the next video. So the next example here, determine the Laplace transform of, and we're going to do the same thing that we saw a little bit ago in the book. So I'll write it the way the book writes it. So we're trying to find this, the Laplace transformation of sine of bt. Okay, writing it out like this and writing it the way that we did up here is the exact same thing. This is going to be that infinite integral from 0 to infinity of e to the negative st times our function sine of bt dt. Okay. This is, believe it or not, something that we have seen in class before when doing this antiderivative. This you're going to have to use integration by parts twice, and then it's going to kind of be like a snake, and it's going to chain back on itself. So let's just kind of go through it. So as we're going through it, first thing we need to do for integration by parts is we're going to set a u, and then we're going to set a dv. Our u, it does not really matter which one you set it to be. I'll let the u be sine bt just because that seems to be a little bit easier to take derivatives of. And then dv, I'm going to let that be the e to the negative st dt. Okay. We also need to find then the du and then the v. Du is the derivative of u. The b is going to come out, and then the derivative of sine is just cosine. Okay. The antiderivative of dv is that we're going to bring a negative 1 over s. That's coming down from the exponent, and then we're going to leave it alone, e to the negative st. Okay, so integration by parts is that this integral, and I'm going to have to keep writing it all out, so the integral from 0 to infinity, just copying this left-hand side down, is going to be equal to the integration by parts. So u times v, I'll write that as negative 1 over s, e to the negative st, sine of bt. Okay, and that's going to be minus the integral, still from 0 to infinity. This term out in front we're also going to have to take from 0 to infinity, of v du, so negative 1 over s, e to the negative st, and then du is b cosine of bt. dt. Okay, so we'll keep going, right? Because we're going to have to do another integration by parts. So we're going to have to set a u and a dv. I'm going to let u be the same thing, but now u is going to be cosine of bt. Du, or sorry, not du, dv, I'm going to let it be the same thing as well, just that e to the negative st dt. So notice that I don't have the 1 over s and I don't have the b, and that's just because we're going to factor that out to the front. So we'll just do that in the next step here. I also need to take my du and my v, but hopefully you can just kind of see what those are based on the stuff that we just did from the top line without me writing it all out. So this is what we have now. We still have the left-hand side of the equation over here, the integral from 0 to infinity, still the e to the negative st, still the sine of bt dt. That's still equal to this here. So we're just going to copy this down, negative 1 over s, e to the negative st, sine of bt. Okay, and now this we're going to do the integration by parts, but remember we factored out a b and then the 1 over s, and the negative signs have canceled, so it's a plus b over s that's now in front of this integral, and then we're going to do the integration by parts, which is u times v, which is going to be, remember v is up here, it's the same v that we get from this one, so negative 1 over s, e to the negative st, times u, which is now cosine bt, minus the integral, still from 0 to infinity, of v du. So v, again, this thing again, negative 1 over s, e to the negative st. Du is going to be the derivative of this u here. We just have to be a little bit careful because it's negative b sine of bt. Okay. dt. Close the bracket. Great. All right, and now we just have to kind of simplify this down even more. I'm going to leave most of this stuff the same, so I'm just going to copy it all down again. Left-hand side is not changing. This term I'm not going to change either for now, so negative 1 over s, e to the negative st, sine of bt. Okay, I'm going to distribute the b over s onto these two terms. So b over s times negative 1 over s is negative b over s squared. We still have the e to the negative st. We still have the cosine of bt. And I'm also going to multiply the b over s onto this. This has 3 negatives now, so it's still negative. B over s, and then it's going to pull out another b over s, so now it's b squared over s squared. And then we still have the integral. I'm just going to leave the integral alone. Integral from 0 to infinity of e to the negative st sine bt dt. Okay, cool. Now is the trick part, right? Because I have the integral e to the negative st sine bt on the left, and then that same integral e to the negative st sine bt on the right. I'm going to add this entire term over to the left-hand side. When I add that over to the left-hand side, I have a 1 from this integral, and I'm going to add onto that b squared divided by s squared from the other integral. And now still have the integral. All right, that's going to be equal to the right-hand side, which we can clean up a little bit by factoring a 1 over s, a negative 1 over s, I guess, and an e to the negative st. That'll leave us with just sine bt plus 1 over s cosine bt. Last step will be dividing by this 1 plus b squared over s squared. And we're also going to clean it up like quite a bit at this point. So multiplying, or I guess dividing this over and then cleaning it up, we get this. So we still have the integral on the left-hand side from 0 to infinity, e to the negative st sine of bt dt. But now on the right-hand side, when you divide this all over and simplify it out, we have that e to the negative st, and this is going to be divided by an s squared plus b squared times negative s times sine of bt minus b times cosine bt. All right, and then don't forget, we are still taking this. This is now the antiderivative, and this is going to be going from 0 to infinity, just like before. If we plug infinity for the t values into this, e to the negative st should really be in the denominator. These are going to bounce back and forth between -1 and +1 forever, but this dominates. So when I plug 0, or sorry, not 0. Whoa, what did I just do? Stop it. Go back. All right, so if I plug infinity into all of this stuff, everything just goes to 0. Minus, if I plug 0 in for all of this, e to the negative st is going to go to 1. Sine of bt is going to go to 0. Cosine of bt is going to go to 1. So we end up with just the 1 over s squared plus b squared, and we end up with a negative b. So it's negative b over that s squared plus b squared. The double negatives cancel out. This is our final answer here, b over s squared plus b squared. We also have to worry about what values for s does this exist. This exists as long as s is greater than 0, because it's defined everywhere. Okay, I know that's a lot, and it is, but I will go ahead and tell you now that the majority of the time for these nice values, there's just going to be a table that tells you what the Laplace transform is. So you'll just look on the table for sine of bt, and you'll see that the Laplace transformation is b over s squared plus b squared. But this calculation is where they are getting these Laplace transformations from. There's a couple more examples and then definitions here in this section 2 that I want to talk about, like quite a bit. So we're going to make some more videos just for section 2 here.